Here's another way to say optimize. Find the extreme values of f of x, y, z is equal to the natural log of x squared plus 1 plus the natural log of y squared plus 1 plus the natural log of z squared plus 1, subject to x squared plus y squared plus z squared is equal to 12. Now, while the constraint equation is a circle, or a sphere, of radius square root of 12, this doesn't have a physical situation or a physical meaning really, because we have a function with three input variables, x, y, and z. The output would be w. This exists in R4, maybe space-time, but it doesn't exist in a place that we can visualize. Even though our objective function and our constraint are functions of three variables instead of two, the idea that del f is equal to lambda del g still applies. First, let's find del f, and it is going to be 2x over x squared plus 1, 2y over y squared plus 1, 2z over z squared plus 1, and del g is equal to 2x, 2y, 2z. So setting up the equations given by del f is equal to lambda del g, we have that 2x over x squared plus 1 is equal to 2 lambda x. 2y over y squared plus 1 is equal to 2 lambda y. And 2z over z squared plus 1 is equal to 2 lambda z. Let's back up just a little bit. I forgot to mention that we are working under the assumption that del g is not equal to the 0 vector. Therefore, since del g is 2x, 2y, 2z, we know that x, y, and z cannot be 0 simultaneously. However, we note that x equals 0 is a solution to the first equation, y equals 0 is a solution to the second, and z equals 0 for the third. So we won't dismiss them equaling 0, they just can't all be 0 at the same time. So these are our equations 1, 2, and 3. And now we see that we have 4 unknowns, right? X, y, z, and lambda. So we need a fourth equation. You know where that fourth equation is going to come from. It's our constraint. X squared plus y squared plus z squared is equal to 12. Now I'm going to take this whole operation and move it over because I think I need some space over here on the right. Sometimes we can find an easy path by letting lambda equal 0. But in this case, because we have 2 lambda x on the right-hand side, if lambda equals 0, then the right side equals 0, which means that the left side equals 0. That would mean that x is equal to 0, likewise y and z, but we already know that x, y, and z can't be 0 simultaneously, therefore lambda cannot be 0. Well, with that out of the way, let's go ahead and explore these equations. If we take this first equation and divide both sides by 2x, then we will get that lambda is equal to 1 over x squared plus 1. Likewise, the second equation, we divide by 2y, will give us lambda is equal to 1 over y squared plus 1. And for the third equation, we conclude that lambda is equal to 1 over z squared plus 1. Something about the constraint equation, x squared plus y squared plus z squared equals 12, tells me that I want to see if I can isolate x squared, y squared, and z squared in these equations we've just written down. And we can. We can say x squared is equal to 1 over lambda minus 1. Y squared is also equal to 1 over lambda minus 1. Folks, z squared is also equal to 1 over lambda minus 1. This is beautiful. We have just concluded that x squared equals y squared equals z squared if none of them are 0. Now, it could happen that one of them is 0, as we've already talked about, or two of them are 0, and we're going to take care of all of those possibilities with the idea of cases. This is how math people separate out possibilities that could occur. For case 1, we're going to suppose that x is not 0, y is not 0, and z is not 0. Because x squared and y squared and z squared are all equal to each other, we can substitute in the constraint equation x squared in place of y squared and z squared. So we get x squared plus x squared plus x squared is equal to 12, which means that 3x squared is equal to 12, from which we can conclude that x is equal to plus or minus 2. It would follow that y equals plus or minus 2 and that z equals plus or minus 2. Now, we could start to think about like, well, x could be positive 2 with y negative 2 and z positive 2, but we don't need to because our original function here, f of x, y, z, is the natural log of x squared plus 1 plus the natural log of y squared plus 1 plus the natural log of z squared plus 1. We don't actually need x, y, and z. We really need x squared, y squared, and z squared. And as it turns out, we can say that f of plus or minus 2, plus or minus 2, plus or minus 2 all turn out to be 3 times the natural log of 5 because, folks, the arguments are all the same, so the natural logs are all the same expression. We have 3 occurrences of them, and there we are. Case 2 is, we're going to say, is the one in which exactly one of x, y, or z is equal to 0. Let's say that it's x is equal to 0. Then we still have that y squared is equal to z squared from the equations that we worked with lambda. And the constraint equation then becomes, say, y squared plus y squared is equal to 0. Remember, it was x squared plus y squared plus z squared, equals 12. I'll fix that. And here we're saying that x squared is 0 and that z squared is y squared. So there it is. Y squared plus y squared equals 12, which means that y squared is equal to 6, which means that z squared is equal to 6. And then f of 0 plus or minus square root of 6 plus or minus square root of 6 is going to equal 2 times the natural log of 7, again referring back to that the argument is x squared plus 1. I'll note here that we get the same result if y was equal to 0 or if z was equal to 0. The remaining case, which we're going to call case 3, is the one in which exactly 2 of x, y, or z are 0. Let's say that x is the one that's not 0. Then our constraint equation, x squared plus y squared plus z squared equals 12, becomes x squared is equal to 12. F of plus or minus 2 times the square root of 3, when that simplifies, is comma 0, comma 0, is equal to the natural log of 13. Now, folks, we have found 3 values: natural log of 13, 2 times the natural log of 7, and 3 times the natural log of 5. We'll need to know which of these is biggest and which is smallest, right? We were supposed to find extreme values. 3 times the natural log of 5, calculator value, turns out to be approximately 4.83. 2 times the natural log of 7 is approximately 3.89. And natural log of 13 is approximately 2.56. Of these numbers, the one that's approximately 4.83 is clearly the largest, and the one that's approximately 2.56 is the smallest. Therefore, we can say that the maximum is 3 times the natural log of 5. The minimum is the natural log of 13.